Hey everybody, it's Mr. Anderson again, and we are today going to talk about section 7.1.1. We're going to talk about the second day of this section, and our goal today is to talk about some of the differences that we experience and what causes these differences specifically in exponential functions, the way they look graphically, okay? And we will one more time use Desmos for this process because it's a really, really good tool for the purposes of visualizing. So I'll show you a couple things in Desmos today, and the everything I am going to show you is replicatable. There's nothing special about what I'm doing. You should be able to copy some of these processes exactly as I'm doing them if you like, and even if you decide you want to take them to the next level, right? There's certainly plenty of opportunities for that, and you can do that and it'll work, right? Okay, so like I said, a continuation of the first 7.1.1 lesson. If you haven't seen that one yet, go back, check that thing out, watch that because it is a worthy watch. Oops, sorry about that. I've got the problem we're going to focus on, 7.4. I did modify it for the purposes of a bit of a video delivery. And what we're going to focus on are the two kinds of graphs we discussed in our first video. And we're going to really highlight some of these discussion points. And I'll also talk about, because some of you guys might be screaming at your computer screens when you're watching these videos, that there are a couple other options for B values. And so for those of you thinking ahead, I'll shed some light on some of those things. But without further ado, let me just kind of pull open our blank Desmos tab here. And I'm going to set this up in a way that involves a slider. And this is very, very doable, not just for exponential functions, but really for any function. I'm just going to type in the generic form that we're given. Y equals b to the x power. So here we go, y equals b to the x power. And the beauty of Desmos is, because I don't have a base here, it'll ask me if I want to add the slider, and it'll plug in that value on the slider for b, and it kind of creates its own variable, and it's really cool. So I do that, and it starts with b equal to 1, and I'm just going to do this. I'm going to just, oops, sorry about that. I didn't mean to turn it off. I was trying to change it to red, make it a little more obvious. Verify, I've got projector mode on, okay. And it starts to be equal to 1, and initially it doesn't look very exciting, but as we discussed yesterday, when b gets larger than 1, we really start to see that exponential growth happening. And so what I can do here, because our job today is to look at values in between 0 and 1, and then values larger than 1. I can adjust this for b just by clicking on it. So I'll go from 0 to, I don't know, 10. And it'll go continuously unless I adjust this. I can tell it to count by integer values. I can tell it to count by tenths, any step. But I can click play, and it'll move, like I said, continuously in between those values. And you can start to see that happen where we shift from a growth function to a decay function, then back to a growth function, etc. So real quick, I'm just going to kind of pause this. And we're definitely in a situation where b is larger than 1. And I'm just going to make some notes here as we're going through this. It says, hey, how can you describe this graph? And my graph looks something like this. And the language we really want to get to for our purposes is increasing. And really, it's very common to say things like exponential growth. Okay, and so if you're using that kind of language, you're really doing it right. And the alternative, the other thing that we're given here, is a value of b that's in between 0 and 1, like a rational value or a fraction, decimal, something like that. And I'm just going to drag this, right? This is the other nice feature about a slider, down in between 0 and 1. And look at the way that graph changes. I've got like a reflection of that graph. It doesn't look like the growth graph, it goes the other direction maybe. And there's just my quick sketch of that. And you might call this then, if the other one was increasing, you might call this one decreasing. and not exponential growth, but exponential decay, right? Those are some descriptors that we would use to talk about those graphs, okay? I'll change B to be a value larger than 1 again. 4 is certainly good enough. And the next question says, hey, what happens when x gets larger? What happens when x gets smaller? So I'm going to tackle this part right here first. Well, I notice as x gets larger, right, as I read from left to right, the y value gets extremely large very, very quickly. So as x increases, y increases as well. And yes, there we go. Increases as well. And like I said, specifically, like very, very quickly. So I'm just going to make a note of that. All right. But as x decreases, so like consider us like working now from right to left, as x decreases, y also decreases very quickly. As x decreases, y decreases as well, and also very quickly. Okay? Worth noting. Now, I'm going to just kind of back up, and I'm going to look at the decay function, and I'm going to ask the same question. So let's adjust this toggle on the graph. Okay, a half, or, well, 4400ths, or approximately 4/9, is going to work just great for creating that decay function, right? I've got a value in between 0 and 1. So what's happening as x gets larger, look at what's happening to y, right? This is decreasing, so almost an identical statement, but certainly not the exact same. As x increases, we notice that y decreases. And it starts increasing very quickly, decreasing very quickly, but it kind of like, especially if you refer to the stuff from yesterday, it decreases, kind of slowly toward the end. So maybe just something to, take note of. And then, of course, if we work the opposite direction, as x decreases, now as we read from right to left, we notice that y increases very quickly. As x decreases, we notice that y increases very quickly. Okay, and I apologize for my sloppy handwriting, which is why I'm trying to be audible with all my words here. So if you need to back up to listen to any of that, feel free to do so. The next question that we're asked, the next discussion point that we're asked to think about is, how does changing the value of b change the graph? What aspects of the graph do not change? Well, real quick, let's go back to, make this specifically a growth function. So we're going to say from 1 to 10. Okay, and if we change b, notice what's happening. The graph, as b gets larger, the graph is kind of like increasing in its steepness. But there's one thing that is very obvious to me is staying the same, and that I'm wondering if you guys see it as well. Do you kind of see that fixed point on the graph? Do you guys see this here? Okay, as b increases, the graph certainly changes like its steepness, I think we can say. The graph rises very quickly as it crosses that y-axis. However, the constant is that, what's called that y-intercept. So I'm just going to make that note. As b increases, the graph grows in steepness, but the y-intercept is unchanged. Trying to fit it all on there. Okay, but the y-intercept is unchanged. Now, I can do the exact same thing. I can come back here. I'll pause this. I'll change this to be from 0 to 1. So we are specifically only dealing with decay values. I can press play. And now what do we see? Well, as B gets close to 1, we see a pretty flat line. As B gets close to 0, we see, wow, a pretty steep decay function. Okay, I'm going to try to write that. I think I can. As B moves towards 0, the decay function gets steep. But I think you guys notice, and I'm going to just show you what I wrote there. Okay, I think you guys notice that one more time we're dealing with a situation where the intercept, the y-intercept, sorry, remains unchanged. Okay, the y-intercept remains unchanged. All right, are there any special points? Can they be explained in the equation? Certainly that y-intercept is a very, very special point. Here we notice that it is 1. I'll put this back to be the values from 0 to 10, so it shifts from growth to decay and back. And now maybe you're kind of trained, your eyes are trained in on that y-intercept. The question, though, is can this be explained with this function? And the answer is yes. But we maybe don't have the tools yet to do that. If this was our second or third nonlinear function, we might have the tools to conjecture where that y-intercept comes from. But maybe now we don't necessarily have the tools, unless, of course, you remember back from our rules of exponents what anything to the 0 power is, right? Because that's of course where the y-intercept occurs when x is 0, right? And so if we're talking about to the 0 power when x is 0, where could that where would that cross, right? Okay, anything to the 0 power is going to be 1, right? Okay, last thing we're going to talk about here is, does the graph have any symmetry? If so, where? I'm kind of, maybe a little torn on here, and you maybe have to do a little thinking on your own on this one. The reason I guess it looks like it could have symmetry is because there is a reflection of a growth function that is also a decay function. And as we grow in this space, talking about how these functions work, we're going to realize what reflection, and I'm kind of trying to hint at something with my hands here, what is going to create that reflection that creates that symmetry. And there's a couple different lines of symmetry based on, some things that are going to ultimately go into the equation that we don't have necessarily yet. So I will say for this answer right now, I don't know that we have enough to answer this yet, but there's potential. And if you want a little hint, I'll just do something like this. Here, let me pause this, and I will, I don't know. How about we just make this be 2, and then I'll add another one here, but instead of using base B, I'll use base A. Okay, that's going to work out just fine. And it'll say, hey, do you want to add the slider for A? I say, sure. And then I'll take this and I'll make it like that. Oh, that was close. There we go. Oh, shoot. It was really close. Okay. Now I think you maybe can see some of that symmetry happening. And the thing that I will leave you with is, why is that symmetry occurring, right? What connection can you make, okay? As far as some review preview goes here, there are a couple problems that we are going to ask you to try. And ladies and gentlemen, remember, we're asking you to try these things because trying these things will lead you to some questions. And the questions coming out is a good thing, right? That's how we learn, right? So don't be afraid to try. Don't be afraid to get stuck. And don't be afraid to ask questions. Ladies and gentlemen, thanks for watching. Have a great day.